Okay, let's get started. So, as a reminder, we introduced these 6 electrophilic aromatic substitution reactions where we substitute one of the hydrogens on our benzene ring for one of these different groups here. All right, we can do the bromination, chlorination, so we can halogenate that benzene ring. We have our nitration reaction where we put a nitro group, our sulfonation reaction where we put a sulfonic acid group, and then our 2 Friedel-Crafts reactions that create new carbon-carbon bonds, one to an alkyl group and the other to that carbonyl carbon. And then we started mixing and matching these reactions here. So we wouldn't just do one of them. We would do, let's say, the fuming first, and then second, follow that up with the bromination reaction. And we would get a different product depending on the order in which we did these reactions. And that's because some of our molecules are, some of our functional groups on there are electron withdrawing groups. Those electron withdrawing groups are meta-directors because they take electron density away from the ortho-para position. So now only the meta position can act as the nucleophile. And other groups are electron donating groups, so they're ortho-para directors because they lend electrons to the ring, and that leads to this excess of charge density or being better nucleophiles at the ortho and para position. All right, so when we mix and match these reactions, we get these different products. So that's where we're going to sort of start, is just with some practice here. So I got 3 sets of reactions here where I'm not doing 1, but 2 electrophilic aromatic substitution reactions, and you're going to take a second and fill in the product for each of these here. All right, you do the first reaction first, then you got to figure out whether you have an ortho-para or meta-director, and you do the second reaction.
That gives you the HSO3. Yeah. I thought you were talking about the top one.
Well, I did. Your homework due. Oh, the synthesis strategies. Yeah. Oh, you got it done?
Oh, I got to the ones where it has like 3 coming out
That's
of
what
them,
we're
and
gonna
I
do.
didn't know what to do.
That's where we're going with this.
Yeah. Okay. Yeah. I started them and I was like, I don't know what I'm doing. just so wait for the first one. No, it has to. No, but that's if it came first. You're looking at like what reactant came before. Oh, no, I was talking about the first one specifically. I couldn't remember if that one is with the para or meta.
Carbonyls
Yeah.
are electron withdrawing. So we pull that density onto that oxygen.
Yeah, so it would be.
We got this, bro. Easy peasy, man.
Yep. Eyes closed. On the exam, do you want us to write like the
ETA.
whole structure, or is it okay if we give you?
For like the NO2 and stuff, that's perfectly fine.
Okay.
Yeah. You know, you should be prepared for me to, if I ask you what the Lewis structure is, you want to be able to do it. But if it's just a problem where that's a product, you can just write the abbreviation.
I just put no task. Hey, John, NO2.
It's the nitrogen double bonded to oxygen. What? I need to get focused
The
on.
aluminum chloride's always like pulling off one of the chlorines.
I think so, yeah.
It's a methyl group.
That's what I was double checking in my notes right now.
Because
methyl was the parent.
So
No,
meta,
it's
so
also
then.
because there's no.
Where's the parent? It's the one that's weird. That's why that's because hyperconjugation. The weird quantum.
Weird quantum whatever.
That's enough. That's perfectly fine.
Yeah.
A weird quantum effect is what I said, but like that's all you need to know. Weird quantum whatever. Okay. So let's start to go through these here. So in each one of these, I'm substituting a hydrogen on my benzene ring for one of these different groups. All right. What you'll note is that we use this aluminum chloride catalyst a lot, and what it's doing is just removing a chlorine from your substrates here, creating that carbocation that allows us, or rather allows benzene to be a nucleophile and attack. So we're going to bond at that carbonyl carbon to our benzene ring. All right, now my next reaction is a nitration reaction. It will add a nitro group, but the question is where? Where on this ring am I going to put my nitro group? All right, and the nitro, the incoming substituent, doesn't get to decide. It's what's already on the ring. So this carbonyl group right here is going to decide where that nitro group goes. All right, our carbonyl group is our classic electron withdrawing group. It is a meta director. Okay, just to kind of remind you, we talked about these categories, and importantly, our ortho-para-directors are the ones that are kind of easy to spy because you have these lone pairs next to the ring in each of them, so that's a good indication, or it's an alkyl group because, as we discussed, that weird quantum effect we call hyperconjugation makes it an electron-donating group. All right, so if it's not one of those, right, we also looked at our meta-directors. And our carbonyl compounds were those meta-directors, right? Able to pull electron density away from that ring and up onto that oxygen, all right? We also had some oddballs here. Our sulfonic acid group can do the same thing as a carbonyl. And then we have our strong deactivators. These are kind of the ones we just have to know. Our nitro group, an aminium rather, and then if we got a carbon with a bunch of bromines on it, all right? So all that to say that's a meta-director. So that means it's going to direct that incoming substituent to one of those meta positions. So that's where I'm going to have to put my nitro group. Okay? Same thing down here, same game. Do our first reaction. This is now a Friedel-Crafts alkylation. Again, aluminum chloride is going to remove this chlorine, creating that carbocation. So we stick a methyl group on that ring. As we noted, alkyl groups are ortho-para directors. So it's going to direct to its ortho and para positions. All right. We'll then get a mix of adding that next group to the ortho position. This is a sulfonic acid group we need to add with our fuming sulfuric acid. One to the ortho position, one to the para position. Okay. Notice how when I'm doing my abbreviations, this is kind of the one place that you would maybe, I don't know, get into trouble using these abbreviations. We can just use this for our sulfonic acid group. We don't have to draw out the full Lewis structure. I do always bend over backwards to make sure that I'm showing the correct atom is bonded to that ring, right? Where you would get in trouble is if you tried to do something like SO3H. That's not correct, right? Because it's not a hydrogen that's bonded to that carbon, it's my sulfur. So again, I just kind of bend over backwards to make sure I have the correct atom bonded to that ring when I use my abbreviation. All right, and then the last one, and this is going to, these are here to just kind of demonstrate how that order is really important. I'm going to take the same two reactions, but do them in a reverse order now. So now I'm adding that sulfonic acid group first, and my methyl group second. But now I'm looking at the properties of this sulfonic acid group, and it is a meta-director. So it's going to direct to its meta positions. All right, so I'm going to get a different product than if I did these in the reverse order. All right, same two reactions, but the order matters. Cool. All right, so now we're going to complicate things by throwing a third one in here. So now we're going to do a third step where we're going to chlorinate this ring. And same sort of problem. We got to ask ourselves, where is this incoming substituent going to go? Now we have two things on the ring here. And we just have to consider what both of them are doing. We established that this was a meta-director, so it wants to direct the incoming substituent to its meta position. This nitro group is what? Orthopara or meta? Is also meta-directing, so it wants to direct to its meta position. And it turns out that they're in agreement here, all right? So both of these functional groups are going to direct that incoming chlorine to this specific carbon. All right, let's play that same game here. Make some more room for myself. We'll consider these two one at a time here. Let me just get you. All right, we're going to do a third reaction. Okay, let's do that bromination reaction. All right, well, my alkyl group we established is an ortho-para director, so it wants to direct to those positions, ortho-para to it. All right, this one's already blocked up, so I'm going to take it away. And our sulfonic acid group is what? Meta-director. And where are the positions that are meta to that sulfonic acid group? Right, this would be its ortho positions, and these would be its meta positions. So we're going to direct to those positions. And these are, again, in agreement. So they're both going to be putting that next group on there. These are distinct positions, right? I would get a different product if I put my bromine here than if I put it on the other side. So we're going to make sure to include both. All right, so I get one product here. And the other product with that bromine on the other side. Okay? So now I want you to play that same game with our second one over here. If we were going to take this molecule and do that third reaction, what would our product be? All right, again, we already established, and we have it highlighted here, that that methyl group is an ortho-para director. I'll take that one away since that site's already occupied. All right, figure out where that sulfonic acid group is going to be trying to direct. All right, we said it was a meta director. The positions that are meta to that sulfonic acid group, again, right next door are its ortho positions. These are its meta positions, so again, they're in agreement here. These are now two identical sites because of the symmetry of this molecule, so I would just draw one additional product. All right, so we have to consider the ortho-para or meta-directing of the first thing on the ring, and also the ortho-para or meta-directing of the second thing in order to place our third. Okay, now in both of these examples, those first two steps, those first two functional groups, they were in agreement. They were trying to force the incoming substituent to the same carbon. But what if there's a conflict? All right, let's do an example here. And let's just be good and kind of label this for our notes here. Conflict between directors. Okay, let me just grab a benzene. So this is going to be a benzene ring where we already have two substituents on here. And now we're going to do a third reaction. All right, we're going to do a Friedel-Crafts alkylation reaction. Okay, our nitro group was which one? Ortho-para or meta? Meta, so it's going to want to direct to its meta positions down here. And our sulfonic acid group, also meta, so it's going to want to direct to its meta groups. Right, and now we have a conflict between these two directors. My nitro wants to put that alkyl group down here, and my sulfonic acid group wants to put it up here, right? So for this, to resolve this conflict, we're going to have to go back to our categories here and note that we hadn't really put this into play yet, but we have these different categories of being either moderate meta-directors or strong meta-directors. All right, so we noted that both of these were meta-directing. But let's note here that our nitro group was in that category of a strong meta-director. And our sulfonic acid group was in that category of being a moderate meta-director. All right, so who do we think is going to win? The strong or the moderate? The strong, right? So that's the key here. Whenever we have a conflict between our directors, the stronger one wins. All right, electrophilic aromatic substitution reactions, just like weightlifting, right? The stronger one wins. So we're going to put that incoming substituent in the meta position of that nitro group. I wanted to do this particular alkylation reaction to also make a separate point, which is that in these Friedel-Crafts alkylation reactions, again, this catalyst is pulling this chlorine off, forming a carbocation. So it's going to be this carbon here that's attached to my ring, right? In that position that's meta to my nitro group. All right, so that carbon where your halogen is where your carbocation forms. That's what's going to be attached to our ring. All right, so given that, we're going to go back to this one up here, and we're going to add a third reaction to it. Let's do just another chlorination reaction. All right, and so given what we just discussed, see if you can't tell me what that product is. All right, sulfonic acid group, a meta director, wants to direct to its meta position. Our alkyl group is what? Orthopara. So it wants to direct to the positions that are ortho and para to that alkyl group. But now if we go in and put our designations, that alkyl group is a weak ortho-para director, whereas our sulfonic acid group was a moderate meta-director. So which one's going to win? That sulfonic acid group is stronger than that weak ortho-para director, so that's where my chlorine's going to go. All right, where the sulfonic acid group wants it to, because it's the stronger one. Cool? Okay, so now we can I complicated things last time we introduced those 6 electrophilic aromatic substitution reactions, but then also these 4 reactions here. And these aren't the same in the fact that they're not substituting a hydrogen for a new thing. We're not adding anything new to our ring, but we are transforming something that's already on the ring, converting it from being an ortho-para to a meta-director, or vice versa, from a meta-director to an ortho-para director. So we can also sprinkle in these 4 reactions, and they'll complicate things a little bit. All right, so given what we just discussed, we're going to see some big, ugly lists here, and y'all are going to follow this sequence of reactions and tell me what the product would be. Yeah, yeah, that's good. Yep.
I helped him with the question, and we got to the next one. It had a bunch of steps, and he just goes, "Stop dying."
The copy paste is the best freaking thing about that.
Which one are you on? Wait, I have a question. For the third step, that's not entering, like, that's going off of here with the,
Called a benzoic oxidation.
okay.
So if it's oxidation, what would you do to that carbon?
Oh, the diamond shape, like, that's what I was.
Yeah, so these are oxidation reactions, right? So we're adding more oxygens onto that carbon.
Yeah.
To make your carboxylic acid. Yes.
Yeah, I was just making sure it was carboxylic acid,
Yeah.
and I was remembering that
Yep.
correctly.
No. What? No. You have all the right things on the ring. They're not all in the correct position.
Oh, I lied to you. They were strong.
Yeah. Yep.
Once, because they're, this one's gonna be
So that's what you get two structures.
para,
Yep.
and this one's meta.
Yeah. You got a conflict.
Yes.
Okay.
Oh, wait. But.
So now you gotta look. You gotta figure out strong, weak.
Yeah.
You know.
Yeah.
What happens if they're both?
If they agree, then it doesn't matter.
Okay, would it be both then?
Yeah.
If like it's both meta, but you have to do like both of the different meta positions. How it's like relative
Yeah.
to.
I think you did the same structure. Oh no. Yeah, you do need three. Okay.
Oh, there's only one.
You got it. This one would be which one? And so these are the ortho positions to both of those. Where is it? Where are their meta positions?
That's so true.
No, you skip one. O N.
Oh, it says that highlighted, okay, yeah.
Is that right? Because these are like both moderate meta directors, so it just kind of falls in the meta for both of them.
Yeah, exactly.
Dope.
Yep.
Wait, no, here.
Cool.
Last name.
All right. So, fuming sulfuric acid is going to put one of those sulfonic acid groups on the ring. That will direct to the meta position, that next group, right? Meta director. So here and here. That methyl group But then we do this benzylic oxidation reaction, our potassium permanganate. So that will oxidize, create more carbon-oxygen bonds, that benzylic carbon, into a carboxylic acid. All right, now if we're going to do our last step here, we got to consider the directing of this particular group. Again, that carbonyl carbon directly next to the ring here is a meta-director, and it turns out that these two are in agreement because that is also its meta position. So that last chlorine gets added there. Okay. Starting out with our benzene ring, we're going to add a nitro group. Nitro is a meta-director. So it wants to put the incoming substituent here and here. So that's where my sulfonic acid group is going to go. All right, but we had two of our conversion reactions that had this zinc and HCl, and they were both reduction reactions. So my nitro group gets reduced, so the opposite of oxidized. I replace those nitrogen-oxygen bonds with nitrogen-hydrogen bonds. And to be clear, that is steps 3 and 4, right? This was a 2-step process, which is why they're broken into separate steps here. And my nitro group was a meta-director, but this new amine group is got that lone pair right next to the ring, so it's an ortho-para-director. So it wants to direct that next group here, here, or here. And my sulfonic acid group, also on this ring, is a meta-director. So it wants to direct over here. So now we got a conflict. All right, so now we got to consider their rankings. Our amine group was a strong ortho-para-director, whereas a sulfonic acid group was just a moderate meta-director. So that means that that amine group is going to win, and I'm going to have to draw 3 products here, each one with that last step, that last bromine, in one of those ortho-para positions. All right, so bromine here. Bromine here. And bromine here. Cool. All right, so what we've been doing is mixing and matching these 6 reactions here. All right, and we just want to practice that mixing and matching. Where are my reactions? Hold up. Here we go. Okay, we just want to practice these reactions. So conveniently, we have 1, 2, 3, 4, 5, and 6. All right. And we just want to pick them in a random order down here. So we're going to turn this into a game. All right. In order to decide which one of these 6 I'm going to pick, I'm going to roll the die. All right. So for example, I just rolled a 5. So my first reaction that I would put in here would be this chlorination reaction. I'm going to roll again. Now I got a 1, so my next reaction will be with that fuming H2SO4. All right, so you guys are going to work in pairs here. I'm going to give you some die, and you're going to do this 3 times for a 2-step, and then twice for a 3-step electrophilic aromatic substitution reaction. Okay. What do we got? Pick a die. Whichever one feels lucky. Just one for the 2 of you. You guys, Anthony, are going to work
got the sparkly one. Did you say let's trade? No. Out of here.
Cool. It says you just want to work with that.
Yeah, I got
You
sparkles.
actually can work this, you know, like cable if you want. I don't really
We
care.
got sparkles, so.
All right. You can use my list up here if you want. I'm sure you all have one as well that you could use. I don't really care.
Alright, what do you want first? 3? Okay, so then we got. What the fuck is 30? Okay, should we just do like CH3CL? We don't need to make it all.
Yes.
AL, CL3.
Is this how you play craft?
Okay, 2. We got a 5. 5 is chlorination.
What are they doing?
CL2 is CL3.
You talking about when they grab the
Yeah.
money?
And then we got another
What if they
1.
play on the street?
Okay, I don't like that. We're going again. 2. What the fuck is the 2? Wow, this really likes
They're
paladins.
always rolling dice and movies.
Oh no!
I don't know.
BR2 and BR. Okay, so how do you like this? Because I like to draw like step by step. Okay, so here, let me show them. Because I've been working on this a lot. Okay, so first I'll like have this initial arrow where it's like just like restart, re-end, and then I'll do like another arrow with like each step.
Okay, so
You
we
know?
got the 2 polygons.
CL,
CL2 and
AL,
CR2.
CL3. Grab that.
For the first one.
Okay, so this one we just had. I'm gonna just put the methyl coming off of this one. Oh, okay. And then this is orthopara, right?
Yeah.
So the 2 is gonna
Say
be
again?
CL2, AL, CL3. So that's gonna give us
3 carbons.
3. So it'll be. Wait, so do we need to do 3 different kinds of orthopara? Yeah, that's what I was saying, because I'm doing both. Oh, you know, I guess I don't need to do 3, because that would just be like a duplicate. Okay, and then my last one is
Oh yeah, Dexter. For halogens. So what's the
Well, but it has the option on it.
Yeah.
How are you doing? That's what I was about to. Wait, what? What? If they're both weak and they're both orthopara, then we would only be able to do like the 2 different ortho positions for this
There
one,
would
and
be
then we
2
could do
products.
like 1 ortho and 1 para for this one.
Yeah.
I think we're gonna have a
put
lot
that
of
on the other
products,
side.
because this one's kind of rolled stupid. Okay, so okay.
Like you pick it up,
So
let's flip it
since
over
both
like a
of these
pancake.
are weak, and they would be okay. So this is what I'm thinking. Since they are like the same, we're gonna have multiple products because this one's kind of weird. But okay, so we're gonna have, since it's orthopara, we're gonna have an ortho here. Ortho to this guy.
4.
Okay, and then we need another one of these guys. Because we need something para on this. Shit, wait, there's gonna be so many. Okay, wait, should we go over Casitas? Because I feel like there's gonna be so many products for this.
Well, that would only matter if we're adding something after it.
Yeah.
Yeah.
And then also like you said, like if it's a
Roll the die, right?
pair, like
Two
it's
again.
Annoyingly,
Yeah,
we
this
get a
is
mix of like a bunch of stuff. Let's,
Okay, so it is a bunch of different.
it's a bunch of different stuff. For this one, let's just say squeeze in an oxidation reaction between steps 2 and 3.
Okay. Okay, I'm gonna do some erasing. What? Oh, about how we're supposed to, yeah. That was just kind of my guess of it would just be a shit ton of things because nothing is really beating out anything. Wait, you said an oxidation reaction, right? So that would be, wait, which guy is that?
So there's this other
No,
ortho
yeah,
position.
it's like the potassium permanganate, I think.
Is like different
That's like the
You have it on
ortho,
this ortho side, you
Meta.
need it on this ortho side as well. That's what it is.
or I mean ortho-para. I'm so tired.
Nah.
Pay
I
attention
was
to
not
your-
gonna come. I was probably I was so fucking.
What I needed in here? Oxidation. Okay, so okay, so this guy, oh. So this is what's gonna, this one. So it's, potassium permanganate. So KMnO4. And then, wait, what about wood? Hold up. Yeah, oh, and heat. And then the fourth step would be the bromination, right? And then.
It did. And then we get the CO. So then.
What's your question?
You're in agreement.
You could also just re-roll if you want. But yeah, I mean, the bromine on the ring, it will direct a second bromine to the ortho or pair position.
We get the exact same one but flipped, so I mean. No, they're both. They're both good. Like a possibility.
Yeah, like I said, I like to try to write out like all of my steps so it doesn't,
I'm just leaving.
you're just
I just do
winging
it
it in your head.
almost
Yeah, I can't do that. I
almost
have to write out like each individual step so I make sure I'm not like tripping up somewhere. At least I feel like that's how I'll memorize it better, you know? Dude, I got the 80. Remember how I did the ACS so fast?
That's still a pretty good score.
Finished?
Do it again.
Did you?
Yeah, go for it.
We got this weird one down here.
Okay, so wait, so this one, you then get two of these guys. Because wait, you have
That one, yeah,
right?
that
Only
was,
two.
they're,
Because it already splits to like the ortho pair thing here.
no, so this one I would.
You know, so I
would
think
really
we
ask
might
is 'cause
have
they're
more than
both
two.
weak and both of them are
But let me work through, that's why I like to write it on my steps, because then I can see how many each step makes, or like what each step makes, you
On
know?
step 4, do one of those benzoic like between 2 and 3, add an oxidation.
Okay, because you need, because for this step, you need it for both of them. Because this guy is ortho pair, so
Do it
ortho
again.
and pair. So that's already 2. So then we have
We
So
will,
then
I'll try to
that
figure out how to
turns it
incorporate
into
that
this.
when we do more practice next week. For now, we're just gonna stick with these 6. Yeah.
So should I roll this?
Yes. Yeah, so you got both of those.
Let's take really much to do this crap ton.
Yeah, I won't ask you that. I'll tell you what, stick between 2 and 3, stick one of those benzoic oxidation steps.
But then like you both work out.
Okay, so now I got this, and then we have one last step, which is the bromination.
Meta, so that's its meta position.
That's only.
Which one's gonna, or, okay, so wait, we're putting on the bromine last, I'm sorry. This one would be 1, because these are identical positions. This one here, you're gonna oxidize this. So be careful, it oxidizes to carboxylic acid, so bigger OH group there. Yeah.
I think I got it. Because halogen is weak, and then the carboxylic acid is strong orthopara.
Oh wait.
So we're gonna do an orthopara from the carboxylic acid on both. So we're gonna have a couple different products.
Oh.
Yeah.
No, I was wrong.
Because we need to do like this, and then we need one that's, oh my god, I need to make these smaller and running out of room.
Yeah.
I think I got it.
Yeah, except for after this, the first one, you have another product over here. So these are two from that, but these are both with those two are ortho. You'd also get one where they're para to one another, your carboxylic acid.
You're right.
Okay, and then we need two of these guys too. Because it needs to be orthopara for this one as well. So we're getting 4 total, I think. Does that make sense why? Okay, so then we also need to do orthopara. Wait, we can't even do shit. Okay, so we can only do ortho on this one. We can't even do para. So it would just be like this, I think. Hold on, I'll show you my thought process
Oh,
in
you're saying
like
they agree on the
one
same.
sec.
Usually either one or 3 products.
Okay, so we got, yeah, we have 3 products, not 4, because you can't do para on the other one because the chlorine's already in the para position. So we're gonna get 3 products and it's gonna look like this. See? Well, I think, actually, I'm gonna have him double check. So for this one, okay, so we attach the methyl in there, that's orthopara, so we got that and that, and then you have the oxidations, which turns into the carboxylic acid on both of them. And then you have 3 different ones because you need the ortho position for ortho and para for this one
So wait,
from
wait.
the carboxylic acid.
The last thing we're doing is putting the bromine on?
Yeah, and
Okay,
this
but the
one is
carboxylic acid is
strong.
which one?
It's
orthopara.
orthopara.
No?
No?
Yeah,
It's
there's
not.
no
Okay. Okay, so there's only 2 products? Okay. Jeez, okay, I was really close.
Yeah, acyl group.
Okay,
Yes,
so
there's
it's
not
carbonyl.
Yeah,
That's
carbonyl.
the
Carbonyl.
So
Yeah,
the
yeah.
BR is gonna go here.
And that's.
So, yeah, okay, so you gave me the ortho,
then-
but as you said, it's an orthopara director, so you should have a second one at this step as well, yeah.
And then that's.
Okay.
That's why there's 3.
Oh, so there's only 2. You were actually right. For the, I totally thought it was 3. So then it would just be like that since it's more. Yeah, because you need
Now,
the ortho and
these
the
2
para.
metapositions are not identical.
Oh, so it would have to be one there too. So it is 3.
I said it was made up. That's what I did.
Okay, and y'all, for these, you tend to have either one, when you do, I'm sorry, if you're doing 3 steps, you tend to always have either 1 or 3 products. So that's kind of an easy double check to make sure that you did it correctly. Okay? All right, I want to move on here to the last thing that I really want us to practice, but kind of my goal here was to just prove that you can kind of just mix and match these on your own to study. All right? The last thing that we need to do is not like follow these EAS reactions, but we need to come up with our own synthesis strategy here for creating a molecule. So if we're given a target molecule here, how do we make it from benzene by mixing and matching those reactions that we've been using, right? So this is now one of those problems where I show you a benzene ring, I show you the product, and I say, how do we get there? Okay, so these are our 4 molecules here that we're trying to design. Everybody take a second and tell me what electrophilic aromatic substitution reactions and in what order would we do them?
Wait, so it'd be like that?
The nitration into chlorination.
There you go.
Yay.
Yeah.
Whoa, wait, so it's only like, oh, yeah, benzene.
Methyl.
I actually kind of like just doing these on the homework.
No, it's methyl to the sulfonation. Because it's oral.
Hey, Tony, have you done like Chem 20 homework this week?
Is the free,
On,
Friedel.
just like, is it turning in like our lecture notes?
Yeah.
Oh, just like notes from,
Yeah, Friedel.
okay, like our
So
lecture
yours
notes?
is-
I kind of want to like fix mine because I was. And then the second thing is just CO2, ALC. I'm not writing down the steps for this one.
So it has to be the, well, it has to be nitro to the, I don't know.
And then that is nitro, wait, I did say nitrous, but I don't say
Yeah, it would have to be that.
And then you do the Frito fat, and then you swap the nitrogen with the K and then go for.
That's the that's an oxidation.
Oh,
The reduction is
The
the
methyl is
transition.
orthopara, right? So it'd be, one would be CH3,
the last
3, and then 2.
Use a Frito fat with, it's just a long chain.
Right, when it's just the methyl group addition, that's orthopara. So it would just be like the CH3Cl and then the main Okay, yeah, we could do that. I was just making sure that one was.
Yeah. Importantly, you have to save this one for last, right? Otherwise, it wouldn't get
Yeah.
that.
Huh?
And then for this next one, can I just leave it like that?
I was working
That's
on
it,
it. I
yeah.
went ahead on
Yeah.
these yesterday.
So you are gonna get a second product,
Yeah,
but if
but-
this is what
Because
you're
I
gonna make.
had the whole day
you're
off
gonna do
yesterday
that.
because the tutorial center was
So we
closed
just
and I
use
couldn't
prep
go
then?
into my math class because it was on main campus. So Monday and Wednesday I kind of just had the days off. I did a lot of nothing. Well, I did a lot of work yesterday.
Alkylation.
Okay, so what was our, what else do you have at the bottom of your page there?
So big change, big, what?
Yeah, if you tried to use that method, that wouldn't be your major product.
Are
because
you
you'd have
thinking
that
like add a
hydrogen
nitro
sulfur.
group and then?
So
just
there's
take
another
the
way that
same
we could
print?
do it that would make sure that it's on that first carbon.
Oh, you're so right. You're so right.
So it has to be
Okay,
the
so
Frito
one
fat with the,
would be-
with the, yeah, so it's the acylation
Which one are we
that cuts
looking
off
at?
the town.
The fourth one?
Yeah,
Yeah.
bottom.
Yeah.
And then.
Yeah.
So,
That's something.
if you're talking about an alkylation reaction or a chlorination reaction, no, it wouldn't matter. The problem is that the alkylation is not gonna work to give you that product, because what was our electrophilic species in those alkylation reactions?
No,
Oh, you're talking the
zinc.
zinc for the aircraft.
Okay, I'll tell you, it's a carbocation, and because it's a carbocation, you gotta watch out for those hydride shifts. So if you try to use that
Oh, wait,
method,
and
that
then you
wouldn't
add the
be your
nitro
product.
group
It would
after the
go
methyl,
instead
right?
hydride shift over to the second carbon,
For the
and that's what
it
it's attached
was
to. So
Wait,
you gotta watch
this
out. So
is-
if you're trying to put it
wait,
on the primary carbon like this one, you're gonna have to use a different method.
I kind of remember it like that.
Alright, we have another way of putting an alpha group on there.
So if you're telling me it's like gonna be on the test.
Good indication.
It's automatically this one.
Because, it's in a better position as well for that one. And then you flip over the nitration.
Yeah.
I feel like we should
Nope,
do
last one's not work.
fuming H2SO4 and then do the
Because
nitro
what's our,
group and then
what's our
the.
intermediate there?
This one's for the para O.
Yes.
Okay,
Yeah.
okay.
The problem is that, what's the, when we do these
Yeah, so we do
alkylation reactions,
fuming
what's our electrophilic
H2SO4 and then
species?
the nitro group and then the methyl group
Chlorine gets
and
pulled
then.
off by the aluminum
flip it,
chloride
yeah.
and leaves what?
Let's not showing up to class.
Now, I'm gonna take off that chlorine, take that pair of electrons away from that
Fuming,
carbon.
nitro group.
I realized listening to.
Like, here. What would be the product of that step there? This thing's gonna jump over here, that bond's gonna break, what would I do left?
That one
And
is,
then
and no, that's what I was doing.
There you go, and so, what do we call the
Tony, is this
come
what
up
you
with
have?
a different method of putting that alkyl group on there.
Oh, damn. Oh, I forgot the study was up, so.
Yeah, you have to put the sodium hydroxide
Yeah.
in there for the flip thing.
Oh.
So this one's tricky.
Also,
These alkyl, you know,
you're
everybody,
missing
my bet is
the-
everybody's gonna try to do an
this-
alkylation reaction. The problem is
Yeah,
those
I did the,
alkylation
okay,
reactions
so for
have
this
those
one, I did the
carbocation
H2SO4
intermediates.
first,
If you
because
try to
that's
put a
metal,
carbocation on that
right?
primary carbon,
And then,
it's
cause
gonna
isn't
shift over to
this
the secondary carbon.
orthopara, but
So
this
this
is
one
orthopara,
actually
this is
you're
strong
gonna
meta,
test
so
the
then
alkylation.
it would go off of
The
this.
method to put an alkyl group
Oh wait,
on
wait,
there.
okay, so
It's gonna have to
fuming,
be in
this
two steps.
is meta, so then we get
This
this
looks
guy,
good.
right?
The important thing
This
I say
guy
is till the
also
end,
meta, so
right?
then
If
we
you
get
try to
this
do
guy.
that
These
right
guys are
after
both.
adding the nitro
And
group,
then
you
you
would
do
do
the
that.
zinc and
Yeah.
NaOH and turn
Awesome.
this from nitro to meat.
No,
Does
right
that make
after.
sense? At least that's what
Wait,
my
is this one?
my guess was.
Is this also Paris or is this made up? Okay.
I think I understand it enough-ish.
But I can also leave it like that and just do that. At the end? Yeah, right? This works?
Oh, yeah, right, you have it like
I
that.
really want to.
So if we really want to attach a primary carbon to the ring, this is the way that we're gonna have to do it, is in those two steps.
One
Because of no
more.
shifts, yeah.
Wait, Chris, I could do it like this too, right?
Correct. Yep, that would be fine as well. Cool, awesome. For this, the reduction ones are where we use the zinc and HCl. So this would be for the oxidation. You want to do the other one, the reduction. This looks good.
Should I add the
How'd you get that sulfonic
halogens
acid?
are repair, right?
Yes.
Okay, well, so it was literally just BaCl2.
So I think you are gonna need this, right? I think you're missing a step up front here. And yeah. Other than that, looks good. Yep.
I got the injector that gave me times 1 mole every 23 for the discharge.
Wow,
Okay,
are you serious?
I think I'm done. I don't even know if I can use I think I can.
So this one.
So that would be in high pressure.
Yeah.
So you might some other product where like
Yeah. More than we had to save this reduction step till the end. We did it right after you put that nitro on there.
Then it would be orthopara, yeah.
This one.
Yeah, you can do that.
Isn't this orthopara?
Yeah. So I get why you said that. This won't actually lead to this product here.
No.
Oh, okay.
Because it's got this carbocation
Oh, that's
intermediate, and that
what it is.
carbocation shifts to that
Yeah.
second carbon.
Wait, so then would I do like a?
There was something I knew that was.
Yeah, there you go.
So there is
Oh,
another way that we
you
have.
put on the with the oxygen and then you take it off with the other thing.
There you go.
Okay, I got you. All right, I know what to do now.
So on this one?
Yeah. So the order of these two wouldn't matter. You would get the same product regardless because they're both orthopara directors. All right. The problem is that when you take this chlorine off, you form a carbocation on that primary carbon. Well, to me, it's going to shift over to that secondary carbon. So if you did these two reactions, starting with this here, your benzene ring would be attached to that second carbon, not the first one, right? Because of that carbocation hydride shift, right? This thing is going to turn into a carbocation before it reacts with benzene. So there's another trick that we have of putting an alkyl group that we're going to have to use if we want it on a primary carbon. All right, so try to use, think about our other reactions, maybe some of those converting reactions. Okay, all right, let's go through these. So these first two are a little bit more straightforward. All right, the second ones are a little trickier. Oops. Okay. So if I want to put the nitro group on the ring, that would be using that nitric acid and sulfuric. If I wanted to put a chlorine on the ring, that would be that chlorination reaction. All right, we're starting with benzene. And I know these are the two reactions I'm going to have to use, but now the question is, what order am I going to use them in? All right. Well, if we look here, we have a meta ring. Our two groups are meta to one another. All right. Our nitro is a meta-directing reaction, whereas our chlorination reaction is an orthopara. So that means I'm going to have to first do that nitration reaction to put that meta-director on the ring. And then I can do my, chlorination reaction. If I tried to do them in the reverse order, I wouldn't get this same product. All right. Similar game down here. Our sulfonic acid group, that's the fuming sulfuric. All right. Our methyl group, we can use our Friedel-Crafts alkylation. Just copy my little reaction arrow. Okay, the question is, what order am I going to do these two reactions in? Fuming sulfuric acid, that would be putting a meta-director on the ring, whereas my alkyl groups are those weak orthopara directors. And since my ring here is an ortho product, I want to do that orthopara directing reaction first. Right, that'll put an orthopara director on the ring, and then I can follow that up with our fuming sulfuric acid. All right, so now the next one. This one's a little bit tricky here, so let's go through. Same thing, let's figure out what reactions we need. Our fuming sulfuric. Our methylation or our alkylation. And then this one, this amine, we don't know how to put an amine directly on the ring. But we can first put a nitro group on the ring using that nitration reaction, and then reduce that nitro group using that zinc, HCl, and NaOH. All right. So the order in which we do these first two reactions wouldn't matter. I could do either my fuming sulfuric. Oh, I guess let's go through the process here of noting that these are both meta-directors. All right. My methyl group is an orthopara director, and importantly, my amine group here is also an orthopara director. All right, so after we reduce that nitro group, we convert it from a meta-director to an orthopara. All right, and my product, everything is separated out here, so this is meta to both this and this. So I'm going to want to put my meta-directors on there first. Doesn't matter what order we wanted to do this. Fuming sulfuric, and then my nitro. All right, but then importantly, if we tried to immediately reduce that nitro group, then we would have created an orthopara director here, which is stronger than our meta-director. So it would direct that incoming alkyl group to these positions here. And we want it in that meta position. So we're going to have to move this, save that for last, and put on that methyl group first. All right. Cool. So importantly, the order of this reduction step, where it falls in here, is going to be important for guaranteeing that you get this particular product. All right, and then this one's a little bit trickier for a different reason. These are both ortho-paradirectors. All right, so we can put our chlorine on. All right, but then what I sort of was betting everybody was going to do, I don't know why I said step 4, is to say, okay, now I just need to put an alkyl group on there. So let's use this alkyl halide with 4 carbons, and then our aluminum chloride, and boom, we'd get our product. All right. This looks like it should work. The problem is that this would not give you this product here. And the reason for that is because of the electrophilic species in our alkylation reaction. All right? So remember, we have this alkyl halide. And what that's going to do is with that aluminum chloride, that chlorine donates its electrons to aluminum and then leaves that molecule. So this would create this carbocation intermediate. Right? Carbocations are our electrophilic species in these Friedel-Crafts alkylation reactions. But what's the problem with carbocations? What do we got to watch out for? Shifts, right? So yes, this primary carbocation is not going to stay. That carbocation is going to jump over onto that second position. So if I tried to do this reaction here as it's written, this wouldn't be my major product, but rather I'd have that sec-butyl group where that carbon is connected to the second carbon, right, where my carbocation has jumped to. The second carbon on that alkyl group. Okay? So now I have to, if I want to have this straight chain here, we're going to need to do it a different way. We do have another way of putting an alkyl group on this ring, and this method will guarantee that we attach it onto that primary carbon, and that's using one of our reactions here that will convert our carbonyl group into an alkyl group. All right, so this will guarantee, notice how now it is on this primary carbon, not on what would have been the secondary carbon. Cool, so that's what we're going to do. We're going to do an acylation reaction, 4-carbon acyl group. And then we're going to reduce it using that zinc, HCl, and heat. Okay, this is a way we can just note here. This is a method to add an alkyl group without any shifts. Cool. All right, we have a little bit more to discuss with regard to this topic. I sort of wanted to space it out a little bit so that you have like your weekend to do your homework and to do your practice, so then we can come and learn and build on that. All right, and then yeah, so we'll continue this next week.